Okay, everybody, video 3 of 10 in the countability series of this week's 12 videos. I'll be talking about some operations you can do on relations. There's two main operations that I'll talk about. Um, Composition and inverse. And then three other ones that are all closure relations. So a closure is when you have a property and you want to make sure something has it, you take a closure with respect to that property. So this is to ensure a property. And let's discuss the closures for reflexivity, symmetry, and transitivity. Okay, but let's start. Nope. Let's start with composition. Okay. Wrong one. In no world is that what I wanted. Thank you. Okay, composition. Composition of relations is how we'll ultimately define composition of functions and is a really big deal. Okay, so all of these properties, I should say up front, these are really about binary relations. It's possible to lift these ideas to other settings, but generally these properties are talked about in the context of binary relations, which are far and away the most common relations. Okay, so the core idea of composition is that it lets us take two relations and stitch them together. So if we have a relation R between types A and B, and another relation S between types B and C, then their composition will relate A and C. That's sort of the stitching together. Okay, unfortunately, there's two different notations for this. It can be written R semicolon S. This is, I think, the sensible, like for English speakers at least, way of doing it. It's sort of the left to right thing where you go from A all the way along to C. Another way people will write it is with this circle notation. This is what people use also for composition of functions. And this is maybe less intuitive where we say S will be composed with R. We'll run R and then we'll run S. In either case, these are more or less equivalent definitions, and what they refer to is the following relation. AC, where AB is in R and BC is in S. To write it in another notation, we would say A RSC if and only if A RB and B RC. So then if we really wanted to quantify it, because we were going to be super careful and specific, we would say for all AC, we would say here exists a B. And then this is the scope of that exists. Okay, so that's composition. Let's draw up an example. So to do an example, I'm going to define a particular set of relations. For our examples, let me do them in, say, red. So R is going to be a relation on a city and a food. Those of you who've looked at the combo homework or are done with the combo homework already will know that someone who wrote these problems is a little bit obsessed. And S relates food and ingredients. Okay, so let me define R. I'm just going to do a tiny subset. So R is going to be the relation Vienna, Schnitzel. Who else? Let's do Philly, cheesesteak. If you are in Philly, you should not eat a cheesesteak. They're terrible. What you want to do is get what's called a roast pork. It is absolutely a superior sandwich. There's also excellent banh mi in Philly if you like that classic Vietnamese sandwich. But anyway, the cheesesteak is a total tourist trap thing. They're just not that good. And then lastly, let's do Puebla City, Ciudad de Puebla, and tacos al pastor. Okay, so there's our relation. Each of these relates a city to a food that that city is known for. Let's look at the relation S we'll use. So this is going to relate things to their ingredients. And I'm just going to have it sort of be incomplete, but we'll say schnitzel is related to veal. Schnitzel is also related to pork. Those are the big two. Chicken schnitzel is less popular, though it's very popular among Jews. But generally in the city, you'll find less of the chicken schnitzel. Okay, cheesesteak. I mean, the really classic question is, do you use whiz or do you use provolone? All right, Provi, as a former fellow resident myself. There's other ingredients in a cheesesteak also, but here we are. And then lastly, just for the sake of completeness, I'll write, Hargau shrimp, though I've had excellent lobster Hargau in Boston. Okay, so with that pleasant, I hope, diversion, let's think a little bit about what we might get if we looked at R semicolon S, R composed with S, which is to say the same thing as S of R. Okay, so what is this relation going to be? What's in there? Well, what we do is we find things. You can sort of draw a diagram that looks like this, right? So we have what? Vienna, Philly, and Puebla City. And then we have some foods. Schnitzel, cheesesteak, al pastor. That wasn't circular enough for you? I'm doing my best here, people. There we go. Beautiful. And then let's look at some ingredients. Veal, pork, cheese with gross. Oh, that's hard to read, sorry. Provi, shrimp. One. I missed some foods here. Hargau. Okay, cool. So let me draw some lines for what R has. R says Vienna is related to schnitzel. Philly is related to cheesesteak, and Puebla City is related to al pastor. Nothing's related to Hargau, and that's just fine. Let me draw that a little better. Right, that's just fine. Okay, here is R. Okay, now let's look at what S does. It says schnitzel is related to veal, schnitzel is related to pork, cheesesteak is related to whiz, it's related to Provi. Al pastor isn't related to anything, though it could be related to pork, and Hargau is related to shrimp. Okay, so what is this relation composition that seems so complicated when you write it down? It's saying jump the lines, just follow the lines together. So let's get our cosmic pen drawing. So what's in our final relation? Well, it's anything that lets us follow two lines, right? Because we go there to there, or we could go there. There's one. Here's another thing. Here's another thing. And then PC, the Puebla City to al pastor, that's sort of dead ends because it doesn't relate to pork. The Hargau, because we don't have, say, Shanghai or I think those are probably really big in Hong Kong too. But anyway, we don't have an appropriate city on the left. Then it's sort of not clear what to do there, right? We're kind of in a stuck spot. So those four lines we draw, that gave us the combined relation. I forgot to write that over here. We have S. So in the composition of R and S, what do we get? I'm going to write the actual answer in black, which will be easier to read. We'll get this relation. Vienna will be related to pork. Vienna will also be related to veal. So it's not a deterministic relation. Philly will be related to whiz, much to its discredit. But it'll also be related to provolone. And that's it. Okay, if we added an arrow between al pastor and pork, then we would add an arrow, a thing in this composed relation between Puebla City and pork. If we added something between al pastor and pineapple, then we'd add Puebla City and pineapple's relation. If we added Shanghai, then we'd have Shanghai shrimp, right? So that is relation composition. Okay, that's easily the most complicated of these. Let me keep going. I'm going to talk about the others. The next one is much simpler. Inverse. So inverse basically just flips a relation. So given R in A cross B, R inverse, that's to the negative 1, is going to be in B cross A. R inverse is equal to that set of BA such that AB is in R. let me put it another way. A R inverse B if and only if B R A. Okay, so for example, what might we get if we took our R from over here, R inverse? Well, that would be Schnitzel. Ooh, that's bad writing. I have much more trouble doing it at the top of the screen. Schnitzel Vienna, pork Vienna. Then what do we have? Whiz, the Philadelphia, Provi, Philly. And then one more, right? Because we would have Al Pastor, Pueblo City. Right? That's the inverse operation. Okay, these are probably the two most common operations people perform on relations. The next most common things people do are the closure operations. So these are relatively quick to explain. Oops, let me do this in black. Let's do closure operations. Okay, reflexive closure. So the reflexive closure is something that takes R in A times A. This is a commonality. All of these are going to work on this assumption that our relation is a relation on a set. R is a relation on A. And that means it's a binary relation where both sides are A. Okay, so the reflexive closure is going to say R but reflexive, right? That's what closure means, right? The foo closure of R is R but foo. Right, so to do this, I'm just going to define a special set. Delta A is equal to the set of AA for all A in the set A. So notice that delta A is like reflexivity. Is German, means original, but it means it's sort of like, this is like the reflexive thing. People call this also the diagonal relation on A because it relates everything to itself. So reflexive closure we define as R union delta A. So it's R, but then add in all of these reflexive entries. Okay, next one. Symmetric closure. R, but symmetric. Okay, this one's not too bad either. R union R inverse. Right? Because if R inverse is the thing that swaps the two sides, this says, hey, if A are B, then B are A. Transitive closure. Okay, so transitive closure is R but transitive. So what we're going to do is we're going to have something like this. So R looks something like this. Right, there's R, there's the elements of A, and R is going to highlight, some set of relations between things. Right, and transitivity says, well, I should be able to follow all of these down. Right, so if to be transitive, right, if I have A, R, B, right, this is the property we need to preserve, and B, R, C, then A, R, C. So the way we're going to do this is by continuously composing R with itself. Solution, compose R with itself. Because if composition, which we defined up over here, is this idea of one hop between two relations, if we keep composing something with itself, we'll get arbitrarily many hops. So what we'll say is this. Okay, let's do a side definition. r to the 0 is going to be delta sub a. R to the 1 is going to be r. And r to the n is r composed with r to the n minus 1. Okay, technically, not strictly necessary to have that case. That's not how you spell that word. Okay, so with this definition, here it is, transitive closure. So this will be written usually R plus, and that's defined as take the union for n, for I, I'm writing in the wrong spot, for 1 less than or equal to I of r to the I. That is to say, this is r union, or r to the 1, union r squared, union r composes itself 3 times, union r 4, union, and so on, right? All of them. And the idea is that this captures the original relationships. This captures all the 1 hops. This captures all the 2 hops. This captures all the 3 hops, and so on. And this is an infinite chain of unions, but if your relation is finite, you'll bottom out and get an answer. Otherwise, you'll get something else infinite. Okay, cool. So these are the operations you need to know. I'm sorry that I don't have concrete examples for these closure operations, but suffice to say this will be enough for you to know about them to do the homework, which is why we're going to stop there. Ordinarily in the course we'd spend more time talking about it, but there sadly just is not time. Okay, I hope everybody's doing well, and I'll have the other videos from the series posted shortly. Cheers, y'all.